Welcome dear students to lecture 1 of module 3 time response of feedback control systems. In the analysis of a system, if the input, output and other variables in the system are represented as a function of time, then the analysis is called the time domain analysis. The output of a system for a given input is the response of the system. In studying the system response of a feedback system, three characteristics are to be known. They are the transient response, the steady state response, and the stability. So to find all these, the transient response and the steady state response and the stability, we need to give inputs, different inputs, and we have to check the corresponding output. So first what we'll do is we'll see the reference input. So there are some standard test signals. Okay, so what are the standard test signals? The most commonly used test signals are unit step signal, unit ramp signal, unit parabolic signal, and the unit impulse signal. So we will in detail let us see how do we represent these signals and what are their Laplace transforms. So first here you can see the step signal over here. So here you can observe the step signal. So what is a step signal? It is a signal whose value changes from one level, usually 0, to another level in a 0 time. So if I write this as R of t, how do I represent this over here? See, step signal is equal to 1 when, that is unit step signal t is greater than or equal to 0. Okay, and it is equal to 0 for t less than 0. Then what is the Laplace of this? So if I write R of s is equal to Laplace of a constant is what? 1 by s. So this is the Laplace of a step signal. So this is about the step signal. Now next is a ramp signal. It is a signal which starts at a value of 0 and increases linearly. Now here we talk in terms of the slope. Now if I consider the unit ramp, so then slope is equal to 1 over here. So here R of t, how do we represent a ramp signal? R of t is equal to t for t greater than or equal to 0. It is equal to 0 for t less than 0. And what is the Laplace? R of s equal to Laplace of t is 1 by s square. Next, the parabolic signal. The graphical and mathematical representation of this signal is shown as below over here. So how do we represent this mathematically? So R of t will be equal to, it is half t square. This is how a parabolic signal is represented for t greater than or equal to 0. It is equal to 0 for t less than 0. And what is the Laplace of this? So R of s is equal to 1 by s cube. This is the Laplace of the parabolic signal. A unit impulse signal is defined as a signal which has 0 value everywhere except at t equal to 0, where its magnitude is infinite. It is generally called as a delta function. It is represented by a pulse of small width but unit area. So here I can write this as delta of t is equal to 0 for t not equal to 0. Okay, as the width a tends to 0 with the area remaining the same, then this function R of t approaches impulse function. So I can write this as also, this has a property of say minus infinity to t delta of x dx is equal to 1. So Laplace of this transform of this impulse function is given as 1. Okay. The order of the system. So what is meant by the order of the system? order of the system. So order of the system means number of closed loop poles. So if you have one closed loop pole, then it is called the first order system. Two closed loop poles, then it is called second order system, so on. Now in this case, let us first find the closed loop transfer function. So C of S by R of S equal to 1 by Ts plus 1. This is the closed loop transfer function. So in this case, you can find that, see here, if I read this is 1 by T whole divided by S plus 1 by T. So here, poles means you have to equate the denominator to 0. So 1 plus 1 by T equated to 0. So what do we get? We get S equal to minus 1 by T. So at the origin, we have one pole here. Okay. So, sorry, we have one pole here. So hence, since we have one pole, it is first order system. If we had two poles, then it would be a second order system. So now next, let us find the response to the step input. Now we have got the transfer function here. Now we need to find the response to the step input. Now let us find the response to the step input. So let me write the transfer function of the first order system. C of S by R of S equal to 1 by T S plus 1. It is unit step input, therefore R of S will be equal to 1 by S. Now let us substitute here for R of S. So C of S will be 1 by S into Ts plus 1. Okay. So now what we'll do is, let us apply partial fraction method to find the factors here. So 1 by S into Ts plus 1. We need to apply inverse Laplace transform. So we have to, so for that, let us apply the partial fraction method. So A by S plus B by Ts plus 1. 1 is equal to A into Ts plus 1 plus B into S. So let us apply this. So if I put S equal to 0, then what do we get? We get A is equal to 1. Next, I need to put S equal to 1 by T minus 1 by T. So if I substitute there S equal to minus 1 by T, I get B is equal to minus T. Okay. So let me substitute over here. So I get C of S equal to 1 by S minus, it is T. B is T divided by, I will take it as S plus Ts plus 1. So this I can write it as 1 by S minus, if I take this T out, it will be T by T S plus 1 by, I can write this as 1 by S minus 1 by S plus 1 by T. Now finding the Laplace inverse, C of T equal to 1 by S Laplace inverse is 1 minus 1 by S plus 1 by T is e to the power minus small t by capital T. This is the output response. Now let us consider the error response. So error response E of T is given by, we know that it is E of S equal to R of S minus C of S. No? Now here in time domain, R of T minus C of T. So here R of t, we know it is step input. So 1 minus 1 plus e power minus t by t. So we get error at response to e to the power minus t by t. So now let us plot this response. Okay. So here see, this is the output response. So this is 1 minus e power minus t by t. And what happens to the error? This error gradually dies down over here. So this is given by e by exponentially decreasing, it is t by t. So now if I write the steady state error, ESS is given by limit t tends to infinity e of t. So if I substitute, what is e of t? E to the power minus t by t. So if I substitute that, I get the answer as 0. E to the power minus infinity will be 0. This is what I get. So steady state error will be 0 whenever I apply a step input for a first order system. So next we will see the time response of the second order system. So second order system means we have two poles. Okay, that is called a second order system. How do you find these poles? We equate the denominator of the transfer function to 0 and we find the roots of that. Those are the poles of the system. Now in this case, first before going into the exactly the time response of the second order system, let us learn some terms over here before that. So here first what we will do is let us find the closed loop transfer function. So C of S by R of S. Here see, g of s is omega n square by s square plus 2. This is called, see, this is called zeta. Okay, this is called as zeta. So zeta omega n s. So c of s by r of s, g of h of s is equal to 1. So after simplification of this we get it as omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is the closed loop transfer function of a second order system. This is a standard form. Okay, this is the standard form for the transfer function of the second order system. The time response of any system is characterized by the roots of the denominator. This is the denominator, which in fact are the poles of the transfer function. So if I need poles, then equate the denominator to 0 and find the roots that will give the poles. The denominator of the polynomial, now this denominator is called the characteristic equation. So it is called as the characteristic equation, denominator of the closed loop transfer function. Okay, so in this case characteristic equation s square plus 2 zeta omega n s plus omega n square equal to 0. This is the characteristic equation. And roots of this I can write it as, these roots I can write it as s minus s1 into s minus s2. We have come across the term zeta. So this I can write it like this, or I can write it as this way. Okay, this zeta is called the damping factor. Now, so there are different values for zeta. Now let us consider the range. Now if this zeta ranges from 1 to infinity, then it is called the over damped system. If this zeta value is equal to 1, then it is called a critically damped system. Accordingly, we can write the roots. I will come to that later. First, let us just see what the values and what is it called. Okay. If this zeta value ranges between 0 to 1, then it is called a underdamped system. And if zeta equal to 0, then it is called a undamped system. So let us see one by one what is the response of a second order system for different values of zeta. Now first I will consider the underdamped system. We'll do for this one. Okay. Let us consider the underdamped response, where zeta value ranges between 0 to 1. So considering the characteristic equation, s square plus 2 zeta omega n s plus omega n square equal to 0. Let us apply that. You know the formula to find the uh, roots of a quadratic equation. Apply that. So applying that, you get two roots. I will write together as it is a complex root, minus zeta omega n plus or minus j omega n root of 1 minus zeta square. For simplicity, what we will do is, let zeta omega n, we'll consider it as alpha, and omega n root of 1 minus zeta square, we'll consider it as omega d. So here the roots will become as minus alpha plus or minus j omega d. Now for unit step input, we know that R of s equal to 1 by s. Now let us consider the transfer function. C of s by R of s equal to omega n square whole divided by s square plus 2 zeta omega n s plus omega n square. Now let me substitute for R of s. So R of s is 1 by s omega n square whole divided by s into s square plus 2 zeta omega n s plus omega n square. So continuing further, since we have to find the time domain response, we have to take Laplace inverse. So we need to apply the partial fraction method. So this plus b s plus c whole divided by s square plus 2 zeta omega n s plus omega n square. So this on what left hand side, it is omega n square divided by s into s square plus 2 zeta omega n s plus omega n square, which is equal to, now here it will be a into s square plus 2 zeta omega n s plus omega n square plus numerator only, it is s into vs plus c. Taking common denominator, that's all what we have done here. S into s square plus 2 zeta omega n s plus omega n square. Now what we have to do is, we have to compare the numerators here. So omega n square, we get it is equal to, let us first take the common terms together, s square into a plus b plus s into 2 zeta omega n A plus C plus A omega n square. So let us compare the coefficients. So comparing the coefficients. So here we get A omega n square is equal to omega n square. Hence we get A is equal to 1. Okay. Then next let us compare the B terms. So B terms we have to compare now. So let us find B now. So comparing again 2 zeta omega 1 A plus C. Compare this for then also we have A plus B is equal to 0. So we know A is equal to 1, therefore we get C is equal to minus 2 zeta omega n and B is equal to minus 1. We know that zeta omega n is equal to alpha. So we'll substitute that over here. So we will write this C of S. We had it as A by S. So A is 1 by S plus we have Bs plus C. So B is minus 1, so minus S plus C. C is minus 2 zeta omega n. Zeta omega n we know it is alpha. So here it is minus 2 alpha whole divided by S square plus 2 alpha S 2 omega n S plus omega n square. Now what we have to do is here this I can take 1 by S. Let me take negative sign outside. So you get S plus 2 alpha whole divided by S square plus 2 alpha S plus omega n square. We have to apply Laplace inverse. Before applying Laplace inverse, what we will do is we will complete the square over here. Okay, so here completing the square, we have to take the denominator. So completing the square. Let us consider the denominator. So S square plus 2 alpha S plus omega n square. So how do we complete the square? See here S plus b, if it is S plus b the whole square, then it is S square plus 2ab uh, 2 yeah a plus b the whole square. What's the formula? A square plus 2ab plus b square. Okay, the same thing here we have S square in the place of a and we have alpha in the place of b. So here I have to take plus alpha square minus alpha square. So applying the formula, I can write it as S plus alpha the whole square plus omega n square minus alpha square. We know alpha is equal to zeta omega n. So let us substitute over here. S plus zeta omega n the whole square plus omega n square minus zeta square omega n square. And also we know omega d is equal to omega n root of 1 minus zeta square. So I can write this as omega d square equal to omega n squaring. Square into 1 minus zeta square. Now taking this above, say if I consider it as equation 1, I can write this as S plus zeta omega n the whole square plus I can take this omega n square common 1 minus zeta square. So this is nothing but omega d square. So I can write this as S plus zeta omega n the whole square plus omega d square. So this will be the denominator. So let us write now C of s equal to 1 by s minus, so we have s plus 2 zeta omega n whole divided by s plus zeta omega n the whole square plus omega d square. Now let us take the, yes, now again further splitting it up. See here, if I directly take the Laplace in 1 by s, I'll get it as 1. But here, see s plus 2 zeta omega n by s plus zeta omega n square plus omega d square. This, I need to have, what do I need to have? S plus zeta omega n only in the numerator to get it as a cos term here, right? So what we will do, we'll split it up first. So I write this as 1 by s minus, this is s plus zeta omega n whole divided by s plus zeta omega n the whole square plus omega d square plus, here what we will do here, it is, see, I will write with zeta omega n divided by s plus zeta omega n the whole square plus omega d square. This is what I get. Now this term will be cos term. But if I want this to be the sine term, I need to have omega d. So I'll multiply here by omega d and divide by omega d over here. Then it will become a sine term. So now I will take the Laplace inverse. C of t equal 1 by s is 1 minus, it is a delayed function here, s plus zeta omega n. So here it is e to the power minus zeta omega n t into, here it is, this is cos omega d t plus, here this zeta omega n, these are constant term, omega d will remain, and here it is, again it is a delayed term, so e to the power minus zeta omega n t, and it is a sine omega d t. Then further I can write this as, I can take 1 minus e to the power minus zeta omega n t term common, and here I get it as cos omega d t plus, we have here zeta omega n. But what is omega d? Omega d is omega n root of 1 minus zeta square sine omega d t. So I can write this as 1 minus e to the power minus zeta omega n t into cos omega dt plus zeta by root of 1 minus zeta square sine omega dt. So proceeding further, C of t is equal to 1 minus e to the power minus zeta omega n t. Let us take that root of 1 minus zeta square common. So here into root of 1 minus zeta square cos omega dt plus zeta sine omega dt. Now we know that we have to apply the trigonometric formulas what we have learned. Sine omega dt plus theta is equal to sine omega dt cos theta plus cos omega dt sine theta. Okay. Now if you consider this triangle like this over here, this is theta, this will be root of 1 minus zeta square This is 1 and this is zeta. So sine theta will be equal to root of 1 minus zeta square, and cos theta is equal to zeta. So tan theta is equal to root of 1 minus zeta square by zeta. Hence, I can write over here C of t is equal to 1 minus e power minus zeta omega n t divided by root of 1 minus zeta square. Okay. So this is what I get this from this formula. No, this I get it from this triangle. So sine theta here. So this we get it as sine omega dt plus theta. This is the final response of C of, that is for the second order response for an underdamped system, step response. So let us draw the step response here. So if this is the time axis and this is your output response C of t, and this is the input, step input, then the response will be in this form. It will peak first, then it will slowly settle down at a steady value. So this is given by 1 plus e power minus zeta omega n t, that is this response, divided by root of 1 minus zeta square, and here negative n. So here this is given by 1 minus e power minus zeta omega n t whole divided by root of 1 minus zeta square. Now the steady state value CSS is given by limit t tends to infinity C of t. It is equal to 1. Okay, you substitute this, you're getting 1. That is, here at this instant, the steady state will be reached and we'll get the desired output.